So as I promised earlier that we'll be uploading some good questions for JEE Main and Advanced. There will be two series. One will be Aura Farming series and another one will be Goated series. The name is inspired from you only because these two code words or whatever the words are very much popular amongst you. So let's start with the first problem. I have taken the problem. This one is this one is a relevant problem for JEE Advanced. So I've taken the problem from the gravitation. So let's start with the aura forming problem one, that is from gravitation, and a mixed concept of, you can say, SHM also. So let's start with the questions. So there is a automatic stabilization of orientation of orbiting satellite utilizes the torque from the Earth's gravitational pull on a non-spherical satellite in a circular orbit of radius r. So this is a circular orbit whose radius is there is a automatic stabilization of the orientation of orbiting satellite. So this is making up a satellite. So now consider a dumbbell shaped satellite consisting of 2 point masses m connected by a massless rod of length 12 much less than r, which where the rod lies in the plane of the orbit. The orientation of the satellite relative to the direction toward the earth is measured by angle theta. So let's understand the problem first. So satellite is stabilizes by uh, the torque from the earth gravitational pull on non-spherical satellite in a circular orbit of radius r. So that means this satellite or this combination, whatever it is, like this is a form of satellite, this is stabilizes due to the torque that is produced due to earth gravitational pull. Now just consider a dumbbell shape. This is a dumbbell shape satellite, and this is inclined. This is inclined with with a vertical angle theta, as shown in figure. The orientation of the satellite related to the direction toward the earth is measured by angle theta. This is also given. So you need to find out the value of theta for the stable orientation. So I'll be concentrating on the first question first, then on the next question. So to make the video shorter, I have already done the calculations. So just understand this one. Whenever this will be in a balanced condition, that means that the net torque should be 0, right? So let's assume this one is L1, this one is L2. So if you apply law of cosine over here, this is R, this is L, so you can write this one as L square plus L R square plus 2RL cos theta, and this one is L square plus R square minus 2RL cos theta. So these two will be the distance L1 and L2 from the center of the earth. Now let's assume it will be attracted towards this one and it will be attracted toward this one. Both the forces will be F because they are equal. Sorry, not equal, they will be F1 and F2. The masses are equal but the forces will not be equal, as F is equal to gmm by r square. So r is playing a vital role. So for this one, if I say this one is F1, so if this is phi, this one will be also phi. So it will have two components. This one will be F1 cos phi, F1 sin phi. Similarly for this one, there will also be two components. This component will not contribute to the torque, only this component will have a contribution towards the torque. Okay, so that's the thing I have done. So this is F sin phi 1. Now this into perpendicular direction, this is the perpendicular direction, that is F sin phi 1 into L. This is the torque, and for this one will be F sin phi 2 into L. So if this is at equilibrium, that means this must be equal, this torque should be equal. So F is gmm by r square. So r is L1 only, and for this L2 only. So gmm by L1 square, gmm by L1 square, and this will be r. Now to replace this phi 1 and phi 2, as this was not given in the question, so I will be using the triangle law of sine law. Law of sine, what is law of sine? The side of a triangle and its opposite angle, or the sine of its opposite angle, will be in proportion. So L1 by this angle, that is sine 180 minus theta, so it will be equal to r by this angle sine phi 1. So you can write sine phi 1 as r sine theta by L1, and L1 is itself this one. So to find out the torque, you can write f sine phi into phi 1 into L. F is gmm by L1 square, sine phi 1 is r sine theta by L into L. So L1, sorry, r sine theta by L1. So this L1 square and L1 makes up to L1 cube. This L1 is this much, so this cube, and in the numerator as I have written as it is, and for the other one this will be minus only, because in place of L1 you will be getting L2. So to have the system or the orientation to be stable, you just need to equate them, so both the torque will be equal. So you can clearly write, so when they will be equal, you can clearly see from the equation this all is getting cancelled out. So this will be equal only when you can clearly see that if this value of theta is 0, because sine 0 will be 0, okay, or pi, or this one will be pi by 2, okay. So theta should be 0 or pi by 2, okay. So if it becomes 0, that means this will be like this one, and if become pi by 2, then this orientation will be this one. So you can clearly see that if this is pi by 2, then earth will attract both towards it, and it will be the position of unstable equilibrium, but it will be the position of stable equilibrium, theta is equal to 0. So if you just equate them, this sine 0 is 0, so then also the net torque becoming 0, okay. And cos 0 is how much, 1, so this total term becomes 0. So at this position, this will be the equilibrium position. Now moving on to the next question. So that the angular frequency of the small angle oscillation of the satellite about the stable orientation is root 3 times the orbital angular velocity of the satellite. So how to approach this one? See, uh, let's assume that you are giving, this is the equilibrium position, right? You are giving a very small deflection to this one. The small deflection is, you may write d theta. So you can clearly write the net torque will be, let's say this one is for this one the angle will be theta plus d theta, and for this one also theta plus d theta, or you know that theta is 0, so just no need to worry about, just you can write this as 0. So one will be gmm by r L sine d theta, and at the bottom this will be 0, that means this will be L plus r whole square to the power 3, and root get cancelled out, just L plus r cube, this only will be there, and for this one r minus L cube, okay. So just I have taken that this one is positive and this one is negative. So from that only how to proceed. Torque, you may write that torque, because you need to bring up the torque. Why you need to bring up the torque? Because somehow you need to find relate acceleration with the displacement, because this is the general equation of an SHM, a with x or alpha with theta. So just write this one gmmrl, just in place of theta 0, this also will be 0. So this will be d theta by r minus L cube minus d theta by r plus L cube. So a plus b into a minus b will be this one. Then gmm by rl d theta, just L plus r cube, L minus r cube, a cube minus b cube. The formula is a cube minus b cube, formula is 2b into 3a square plus b square. This is the formula. I have just forwarded with the formula only. So that will be gmrl d theta 2l 3r square plus l square by r square minus l square cube. As in the question given that the r where the rod lies in the plane of the orbit, and length 12 is much less than the r, so you can neglect this L square term. So I've just neglected this L square term, okay. So how, what I did, in the left side I did I will be for these two masses, as this is L, this is L, so for this one ml square and ml square, so 2 ml square, so I'll be 2 ml square alpha. So m l square m l square will be cancelled out, and this will be uh, and 2 to get cancelled out also. Okay, so this will be alpha equal to 3 gm by r cube d theta. In this place you can clearly just neglect this one, you will be getting r to the power 6. This is just a small calculation, and in the question given that so that the angular frequency of the small angle oscillation of the satellite about its stable orientation is root 3 times the orbital angular velocity of the satellite. What is orbital angular velocity of the satellite? For a satellite, omega equal to root over g, v equal to root over gm by r, and omega will be v by r. So this will be 1 by r. If you take this r inside, so gm by r cube, you can clearly understand that this is the time period of the oscillations uh, of the simple harmonic motion that is produced by the Dumbell satellite. So this is coming 3 times of this one, right? As this is you can write omega dash. So is as this is omega dash, so you can write this as like this, and this is omega only. So omega dash is root over 3 omega. So this will be your final answer. So keep sharing, keep liking. I'll be bringing up more videos like this. Okay, thank you everyone. And one more thing, I must thank one of my student Devarpita, because he suggested me this mechanics sorry this process only, because earlier I was going through Lagrangian method only. I will be bringing up a video on Lagrangian also, but she suggested me this one. So thanks to her also. Okay, thank you.